As we solve systems of equations with differential equations, we are going to need to use what are called eigenvalues and eigenvectors. And this is a concept that comes from linear algebra. So this video is going to quickly review that concept at its foundational level so that we're able to solve our systems of differential equations in our class. So the question is going to be, how do we find eigenvectors? The idea is first we have to find these things called eigenvalues. And what we're going to say is the eigenvalues of the matrix A. A is going to be a matrix with elements A, B, C, D, all lowercase, is found by taking the determinant of our vector A minus the scalar lambda times what's called the identity matrix. Now, that's a bunch of linear algebra speak. What that basically means is we're going to take the determinant, which we've seen before, of the top left, A minus the lambda. Then the top right and the bottom left stay the same. And then D is also going to have a minus lambda. And we're going to set that equation equal to 0. Lambda is then the eigenvalue of this matrix. The solutions, lambda 1 and lambda 2, are the eigenvalues. So for example, if I've got the matrix 5, -2, -2, 2, and we want to find the eigenvalues of this matrix, what we'll do is we'll find the determinant of 5 minus lambda, -2, -2, and 2 minus lambda. Notice we subtract lambda from the top right going down the diagonal. And the way we calculate a determinant is we multiply the diagonals together. So we're going to have 5 minus lambda times 2 minus lambda, and then we subtract the product of the other diagonal, which is 4. And the way we solve for our eigenvalues of lambda is we make that equal to 0. Well, if we multiply this out, and I always kind of go backwards, lambda times lambda, lambda squared, it's positive now. Then we've got -5 and -2 gives us -7 lambda. And then finally, 2 times 5 is 10. Minus 4 is plus 6 equals 0. Which means we can factor that to lambda minus 6 times lambda minus 1 equals 0. And finally, that's going to give us solutions for lambda, by setting each factor to 0, of 6 and 1. So then we would say the eigenvalues of this matrix are 6 and 1. Let's do one more example. Let's find the eigenvalues of the matrix 1, 2, 3, and -4. Again, we're going to set up a determinant where the top left and then down the diagonal gets a minus lambda. So 1 minus lambda, 2, 3, and -4 minus lambda. Multiplying the diagonal, we'll have 1 minus lambda times -4 minus lambda, minus the other diagonal, which is 3 times 2 of 6. And that's going to equal to 0. Multiplying out, I get lambda squared minus a lambda plus 4 lambda is plus 3 lambda. And then finally, minus 4 with a minus 6 gives us minus 10 equals 0. Factoring, we get lambda minus 2 times lambda plus 5 equals 0, which means lambda, our eigenvalues, are 2 and -5. Once we found our eigenvalues, it's quite simple to find what are called the eigenvectors. And there is one eigenvector for each eigenvalue. The eigenvector. What we're going to do to find the eigenvector is we're going to multiply the matrix where we substitute lambda into the A vector. When we had that minus lambda, we're going to plug those in. And then we're going to multiply by a vector which we will call k1, k2, and set that equal to the vector 0, 0, which sometimes we just abbreviate with just the number 0. This middle vector, k1, k2, is the eigenvector that we're going to solve for. And there's actually an infinite number of possibilities for that eigenvector. We're just going to select one simple version of it for our uses. So, for example, we already found out that the matrix 5, -2, -2, 2 has eigenvalues of lambda equal to 6 and 1. That's what we did up in that first example. If I wanted to find the eigenvectors for this, I would first start with the 6. Recall that we found the eigenvalues by taking 5 minus lambda, -2, -2, and 2 minus lambda. So when I'm finding the eigenvector for 6, I'm plugging 6 in for both of those lambdas. 5 minus 6 is -1. And then we've got the -2 and the -2 staying the same. And then finally, we have the 2 minus 6, which is -4. And that's going to be multiplied by k1, k2. And we know the solution's going to be the 0 vector. Multiplying these matrices together, we do row times column to get -k1 minus 2k2 equals 0. The second row times the column is -2k1 minus 4k2 equals 0. Now, one of these equations is a multiple of the other. That will happen every time. So we can pick whichever one of these looks like it's the easiest to work with and solve for one of the variables. I'm thinking the first equation, the green one's going to be easiest to get k1 alone. If I add k1 to both sides, I get -2k2 equals k1. And now what I'll do is I'll pick a value for the complex-looking side. That's really convenient. 1 is usually a convenient number. Unless there's a fraction, then we can pick a number that makes the fraction divide out, and so we don't have a fraction anymore. But if k2 was equal to 1, we would solve for k1 by doing -2 times k2. -2 times 1 is -2. And so now my eigenvector is k1, k2, -2, 1. That is the eigenvector that goes with the eigenvalue of 6. But there's still another eigenvalue of 1. We'll go through the exact same process to find the second eigenvector. We have 5 minus 1 is 4. Keep the -2 and the -2. Then we have 2 minus 1 is 1 times k1, k2 should equal 0. And again, multiplying the first row, we've got 4k1 minus 2k2. And the second row times our column is -2k1 plus k2. And they're both going to equal 0. This time, I think the second equation is going to be easier to work with by just adding 2k2 to the other side. So we've got k2 equals 2k1. And now I'm picking a value for k1 on the more complex-looking side. I like using the number 1. By the way, we cannot use the number 0 because we don't want to have a 0, 0 pair. The reason for that's explained in linear algebra. For now, just believe me, we do not want a 0, 0 pair. We can have a 0 and another number, but that's not going to work out here. If I pick 0 for k1, I get 0 for k2. But picking 1, 2 times 1 gives us 2, and so my eigenvector that goes with the eigenvalue of 1 is k1, k2, or 1, 2. Let's look at one last example of calculating eigenvectors from an eigenvalue. The other example we did was we looked at 1, 2, 3, negative 4, and we found out that it has eigenvalues of lambda equal 2 and negative 5. And again, remember, those came from doing 1 minus lambda, 2, 3, and negative 4 minus lambda. So we're going to plug these eigenvalues into that vector. First, looking at the number 2. Well, 1 minus 2 is negative 1. Keep the 2, keep the 3. Negative 4 minus 2 is negative 6. Times k1, k2 is going to equal the 0 vector. Multiplying, we get negative k1 plus 2k2 equals 0. In the second row, 3k1 minus 6k2 equals 0. Again, I can pick the one that's going to be the most convenient to solve. In this case, it's the first one by adding k1 to both sides. So I get 2k2 equals k1. Pick a convenient value for the more complicated side. k2 is equal to 1, which means k1 is 2 times that, or the number 2. So our eigenvector for the eigenvalue of 2 turns out to be 2, 1, k1, k2. Doing the same thing for our last eigenvalue of negative 5. Plugging negative 5 into that orange expression in the top right, 1 minus negative 5 is 6, 2, 3. And negative 4 minus negative 5 becomes a positive 1, times our k1, k2 has to equal the 0 vector. So multiplying, we get 6k1 plus 2k2 equals 0. And multiplying, we get 3k1 plus k2 equals 0. Picking the more convenient formula to solve for, I'm going to subtract 3k1, and k2 is equal to negative 3k1. Picking a convenient value for the more complex side, we'll pick k1 is equal to 1, which means k2 is equal to negative 3 times that, giving us our final eigenvector of 1, negative 3. So for those of you that haven't taken linear algebra, hopefully this helped you see how we can calculate eigenvalues and eigenvectors. For those of you that have taken linear algebra, hopefully this was a nice review of finding those operations so that we can use this tactic in order to solve systems of linear differential equations.